So we'll start with one or two presentation before we go ahead to those one or two things. I'm very sure we are all learning person. I can see some professors here. So we have to, we are here to teach ourselves and to gather information for better fusion and for research purpose. So we are going to teach ourselves, we learn from each other. This is academic setting. So no knowledge is reserved for individuals. So we learn from each other, okay? So please. And at the end of this presentation, I was discussing with Prof that I don't want us to just come here and go back without serious output. Out of these 2 weeks, we should get serious output from here. Apart from the experiment we are going to perform, because it's already here. Okay.
Please, Mr. Apike, just come on. You and me, please come. Come and sit here.
It's plugged. It's plugged.
Sorry, like I said yesterday, we are overly subscribed for this program. So by noon, we'll try to create more space. So for now, we're just doing this. Okay, that space is free now. Okay, awesome. I saw one other person. His name is Patrick. I saw Patrick walking just now. Patrick.
Let him sit down here now, Abby. Sit down. When Patrick comes, we'll create space for him.
So, sir,
No problem.
the introduction where we try to
No problem. No problem.
Thank you very much. Sorry for the interruption there.
So my name is Dr. Samson Aishida from University of Nigeria, Nsukka. I'm from Department of Physics and Astronomy, with under the leadership of our Professor Fabian Ezema. So we are working together in the same lab. We have our group, Nano Research Group. So that's where we work together in the Department of Physics and Astronomy. We are into series of research. We have energy research, we have medical research, we have environmental research group. So we are working on few things: battery, supercapacitors, material for nanomedicines, environmental applications. So these are areas we are working on for now. So at the same time, we have few equipment in our lab that we are using. Now we have SRD, very good one, SRD analysis. You can send your sample to us if you want to do any analysis on SRD. We have CV, for CV estimation, we have it. We have battery analysis lab. We also have UV, we have FTIR, we have PL, that's photoluminescence. We also have, which other one do we have again? For now, no, we don't have SEM for now. We don't have SEM. So we are working on it. If we get good grants, we'll get SEM. So these are the few equipment we have now. So we have well-established synthesis room where you can synthesize your sample convincingly. We have globus, we have foam chamber, we have oven, We have a machine that we can use for annealing machine. We have all of them in our lab currently. So we brought just few equipment here to perform just few things, because when they told us that they don't have any equipment here, so there's no way you can actually sit inside. Many of us will know how to sit inside very well now. I can see big people here. We have been doing it right. So it's not a new thing to us, right? Am I right? Well, we have stages of this thing. Am I correct? Okay, sir.
Sorry for issue power. If you're on the ground floor, can you please check your room if your AC is on? If it's on, it will affect our scheduling. Sorry. Please check if you're on the ground floor and your room, if you need to stop your AC, let's do that. Otherwise, it's going to have a feedback on the scheduling. Okay, Prof, can you get proceed now?
Thank you, sir. So, how many of us are academic staff? Academic staff? Okay, good. So good. So that we'll know who and who we are talking with. Our intention is to group ourselves into maybe 3 today. We'll group ourselves into 3 and to be coordinated by the academic staff, the senior person in that group. We want us to actually start a particular mini review while we are doing the experiment. We want to come up with a review. Each group should have one thing to do. We want to engage us both during the day and at night, so that we will not just be redundant at night doing nothing. So we want to engage everybody both during the day and at night. Within 2 weeks, we can come up with a very good review work. Just pick a particular topic. If you are 5 in a group, so each person will have a subtopic to contribute. We're going to develop it, we're going to publish it together. It's very, very possible. I'll give you an example of how you go about it. We have some publication review, which is very good. We publish it in a very good journal. So that's what we are going to do after this presentation. So we'll group ourselves into like 5 in a group. Then somebody who's an academic staff will coordinate the group, will be able to guide others who are not in the system. Okay? So that's what we are going to do. And each group will pick a very good topic, which within these 2 weeks, we must deliver something. Within these 2 weeks, we must deliver something. So after this program, we'll fine-tune it, we'll publish it. So while we are working on the experimental work, I prepared 3 experiments which we can work on. After this one, because we cannot finalize it here, there are about 5 stages involved. So the only one we can do here is just the first stage. So after this place, we'll process it further for the other phases before the result can come out. So while we are waiting for this, we'll work on the review. Okay? So which we are going to publish together by God's grace. So please, let's work by that. Today, we are starting the review by God's grace. We'll start the review today. So each group will propose a topic. And we're going to develop it. We'll give subtopic to individual. So all through your night, you are going to be working for the write-up. So we are trusting God before the end of this program, because each group, we are going to present it to us before we leave. We're going to present it to us before you leave. So the group leader will present what each group has done. So we'll now look at it, we harmonize it, and see which journal can we actually push it. So if you are interested in energy, if you are interested in nanomedicine, if you are interested in environment, I think it's better that way. We'll group ourselves in that way. Is that not correct? Who are those interested in nanomedicine? Application of nanomaterials for nanomedicine. Application for energy. Oh, everybody for energy. Jesus Christ. Application for environment. For environment. This is serious. Okay. It seems everybody is for energy. Okay. We'll group ourselves. Any professor here? associate professor, senior lecturer, okay, senior lecturer, lecturer 1, okay, lecturer 2, okay. Okay, it's good that way. So we'll pick number now. Are we? You can put it on if you are ready, if something's ready. I think it's better we group ourselves into 1, 2, 3, 4. You are part of it, sir. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15. 5, 5. Okay? I think we are good to go with that. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You are 5. 1, 2, 3, 4, 5. Okay? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? Group 1, group 2, group 3. So you can select your leaders. You are the most senior there, so you'll be the team leader. Oga will be the team leader. Then, yes, Oga will be the team leader for group 3. So what you are going to do, on or before tomorrow morning, propose a topic. Just from, you can create a WhatsApp group within the 5, 1, 2, 3, 4, 5. Then everybody will contribute, fine-tune the topic, the one that we can actually write something on, a review on. I want us to actually develop it before the end of this program. So each group now, you are automatically part of it. We publish it together. I promise you, we are going to publish it in a good journal. We are going to publish it in a good journal. If you have 1, 2, 3, so 3. We can even put all our name in each one. So you have 3 papers, apart from the experimental one, okay? So that's what we are going to do. And I want us to follow it with all vigor. We will not just come here and be sleeping, okay? We should come here and work. So that's what we want to do. So over to this one. Yes, ma'am. Perovskites. Yes, but Prof, perovskite, is it, can we do that? Perovskite, yeah, it's very good. Yeah, I think Prof will talk on that later, on perovskites, okay? We'll talk on that one. So let's start with this mini presentation. This will guide us on what we want to do. So that's the essence of this, just to guide us through, okay? So I term it Emerging Sciences in Nanotechnology, now and the future. What are we doing now? What is the future of nanotechnology in terms of nanomedicine, in terms of energy, in terms of environment? Okay, next slide. So look at these few outlines: nanotechnology, nanomaterials. No problem? So we're going to look at these outlines, then we'll see what we can actually get from it. What we have been doing, I will present it in our lab, the little way we have gone, the little things we have done. We'll see how far we have gone and the little contribution to knowledge. I'm going to present it, both this one and the next slide. Then Prof will talk on renewable energy, or we'll give a topic on renewable energy. Then we're now beginning to look at what we can do for this program. I really want us to do 1 or 2 experiments which we can develop and publish. So that is the essence of this, because the coordinator really wants us to go beyond this level, not just to come and write something down or prove theory. No, we want to pursue it beyond this level. So we want to sustain it so that next 1 year we can see the output of this gathering, okay? So that's the essence of this gathering. And he is interested in that, so we are also interested. So if all things being equal, we can achieve our aim, okay? So the group now, while we are waiting for the light, you can create your group WhatsApp, and you can collect your number and create your group WhatsApp. Just beginning to interact on what we need to do. So Yes, you can just create. Just put the number. So go ahead. Okay. So the work will be presented based on these few outlines. Go to the next slide because of time. Okay. Now, when we come to research now, you ask question. Question is very important. What do I want to do? You can't just say, you came here for a purpose. What have you come here to do? That will be the question you'll be asking yourself. At the end of this program, you should be able to answer that question. What have I come here to do in Abuja for 2 weeks? Have I actualized the aim? What is the purpose of this gathering? That's the first thing you ask yourself as a researcher. You think, what is the purpose of this gathering? Why did I travel all the way from the north, from the east, from the west to this place? The question is very important. And it's about, knowledge is about you acquire acquisition, about sharing an application by the recipient. We are here today, want to give little ideal of knowledge. When you acquire it, you share. And that's what we are doing now. The little I have acquired, I'm sharing with you. And you also go there and you share with others. Then, application of that knowledge. The little one I've acquired, which area can I apply it? Which area? That's very important. And currently, everybody needs application. Not to just do research, you drop it somewhere, let me just put one thing together. And we need application of that which we have done. Next slide. So, that question should be sounding now. Just beginning to think, why am I here? Now, what do you want to do? Once you have realized that, why am I here? The next question will be, what do I want to do? So it's another question that you need to ask yourself. Number one, physics career is a multi-purpose career. As we have said, you can find it in any available opportunities. There's no doubt about that. Physics is multidimensional. Then we talk about conduct research. Do you want to conduct research? If you want to conduct research, how do you go about it? Talking about training and career development. And that's one of it here, what Dr. Lewis and team are doing here. This is training, is career development. They're training people. Then we talk about what? Departmental and institutional training. And that is what is going on here. This is an institute. And they are doing training. They are training us so that we can become a better researcher. That's about departmental and institutional training. Then we'll talk about meeting. We have what we call scientific or just educational. We have scientific meeting. You can go abroad for conferences, for many things. These are scientific meeting, where you can also get knowledge about what to do. You can have a collaboration. You can relate with people, have an idea, because research is about what? Collaboration. Research is not a thing you can do alone. You have to collaborate. If you want to excel research-wise, collaboration is the key. Collaboration is the key. Now, build new facilities is another point. What do you want to do? To build new facilities or research center, library. This is one. SHESCO, SHEDA, all of them. Mathematical center. It's a research center. They put a facility there. We are trusting God. We have discussed with Dr. Lewis. Maybe in future, a center here, they should be able to propose, to be able to get some of this equipment we can easily use to carry out some of this. In fact, as we are here in this period, we ought to carry this experiment to logical conclusion. Here, it's a center, it's a national center. I see no reason why all these small equipment are not functional here. And these are questions we're beginning to ask ourselves. Next slide. So, if you look at physics generally, the brain behind emerging sciences, we are talking about emerging sciences. So you can see what we want to do. Theoretical physics is embedded in it. Chemical physics. These are options that are
embedded in physics option. We have it, biophysics, molecular physics, computational, physics education, quantum physics, solid state physics, nuclear physics. All of them. Like in our university now, they just approved Department of Nuclear Physics. So henceforth now, we'll be having a Department of Nuclear Physics, University of Nigeria. So it's a new department. So we have different options: atomic physics, nanoscience, atmospheric, medical. You have to fix yourself in one of these and beginning to what? To move gradually. Form collaboration. Look at who is in medical physics. How do you contact them? How do you work together? How do you collaborate? Who is in physics education or chemical physics? How do you contact such a fellow? You're beginning to work. Before you know it, you are moving forward. Next slide. So the diversity in emerging sciences in the world generally looking towards the application of sciences. That's what we call applied science. Application of science. How do we apply this knowledge, this science? One, to the society in terms of environmental application. Water pollution, how do we address it? Agriculture, how do we address it? Energy, how do we address it? We are looking for people who can use these emerging sciences to address some of these challenges in our society: food industry, health industry, engineering, in agriculture. How do we apply it? Next slide. So we are dealing with nanotechnology. We deal with nano objects and materials. It's a process that takes place in the nanometer range. Those of us who have been working with it, we know this is just a background of what we are about to do. So it's predicted to be the main driver of nanotechnology and businesses in this century. Nanotechnology is taking over from others. So it has been predicted. So when we are dealing with nano objects, what are these nano objects? An object that differ from the corresponding bulk materials with at least 1 nanometer dimension. Next slide. So look at it. You can see where we are coming from the macro level to micro. Now we are in nano. The other world, they have gone ahead of us. Some other worlds now, they are gone to pico. Yes. Some other nations now, they are working on pico materials. See what micro can give. Macro, very bulky, at the size of like an apple or an arm of a man, an ant. Micro level, microorganism, all this one. Now at the nano level, you see the DNA, you see like a graphene or this diameter of a nano wire. But the future is here at pico level. We are still managing ourselves in nano level, but the future is going to pico level. If you check some of all those devices you are using now, some of them has migrated from the nano level, they're in the pico level. That's why your SIM used to be like this before. If you see your SIM now, they said micro SIM. Has that also? They are cutting it smaller and smaller and smaller. Very soon now, you discover that your SIM will just be like a flex. You won't see it again. Some smartphone today, you can't even remove the battery again. That also, you can't, unlike before where you open your phone, you remove the battery. Now you can't even remove the battery again. So the world is going somewhere. They want to miniature the entire system. Next slide. So that's where we are working at. Nanomaterials, the key physical characteristics that dictate by the nano object, and they are classified into 2: compact material and nano dispersion material. This nanoscience involves the study of structures and materials on the scale of nanometer, whether in 0 dimension, like nanoparticle, or 1 dimension, like nanofiber is 1 dimension, like nanorod or nanowire in 1 dimension. Then I'm going to show you all the example of all this one. Then in 2 dimension, you have thin film in 2 dimensions. Next slide. So what is nanoparticle? Nanometer size, which is 10 raised to the power minus 9 nanometer. That is nanoparticle. With a quasi 0 dimension, it's similar to dimension. We call it a quantum dot. It is 0 dimension. And they are of magnitude less than what? 100 nanometer. So nanoparticles currently stand as a bridge between the bulk material and at the atomic level. The bulk material, very big, and the atomic level is standing between them currently. Next slide. So the study of nanoparticles is of great interest in the contemporary nanotechnology, advances in some curious areas. Markedly, let's just mention a few of them, like energy, very functional in energy. Now we have what we call lithium battery. We have supercapacitors for energy. These are works of nanotechnology. Currently, supercapacitor for storage. We have lithium-ion battery for biomedical. It's very, very functional. Bioengineering and environmental industries. And mostly they use some of these transitional metals that we have been using, like silver, like copper, like zinc, like titanium, chromium. These are major elements or compounds that they have been using. Very functional. So we're going to come across some of them. Let's go to the next slide. So the one dimension we are talking about now has been very wonderful, especially for some of us who are interested in the energy aspect of it, for optoelectronics, for piezoelectronics transducers, for biosensors, for electrochemical, for ultraviolet light emitting diode, for solar cells, gas sensors, electrochemical nano devices. So these are various ways you can apply your nano materials in all this application. You can choose to narrow your own in a particular aspect of it. Okay, next slide. So these are the various applications of nanoparticles. You can see it here. Energy is very important. Every nation, they are striving for energy. Energy, everybody needs energy. If this center is being energized, let me just put it that way, we will not be struggling with this generator. Am I right? By now, we should have, everywhere here, it should be powered with solar. We should be enjoying free solar everywhere. Powerful solar. That's where we are going. Medical, agriculture, information, industry, consumer, defense. In fact, there was the military, I think they came from Kaduna, I can't remember. Recently, we won grant from US military. Our lab won one grant from them. They asked us to produce nanomaterials for defense and security. They also need nanomaterials. They want to use it for defense. They want to use it for security. How do we do it? I also need nanomaterial that can give a lasting energy. So when a particular soldier is in the bush for days, they sell things that he or she is using. None of them will go off for some days that can last for days. Supercapacitor that can store energy for some days. They are interested in research. Even military, they are ready to pump in some money for you to do research to get output. So, but we need output. So let's go to the next slide. So some of these applications. Now, let's look at this one in industry now. If you look at this wristwatch, is common now. This is called nano watch. It's nano watch. This nano watch is multidimensional. It has various applications. As small as you are seeing this nano watch, it can perform wonders. In fact, some students now in your school, watch them. They are using it to commit exam and practice. You'll be thinking that they just put on a wristwatch. It's more than that. Everything you have taught them is in the hands this nano watch. Last week or 2 weeks ago, I was invigilating an exam. I seized about three. Just press like this. It will bring out everything in your notes. This small wristwatch, it's nano watch. It can browse. You can use it to make call. And I asked the boy, I said, how did you get this watch? He said, my mom bought it for me. How much? He said, 250,000. Wristwatch. And he said, I connected this wristwatch to my heart because I'm having problem. So that wristwatch can actually check his BP as the handwatch. The moment you remove it, the moment I seize it, he says, sir, I'm dying, oh, I'm dying. I said, you will not die. He said, because of this wristwatch, I caught you are using this watch to do something. So he said, if I remove this wristwatch from my hand, that the wristwatch is connected to the phone, is connected to the heart, that his BP is increasing now the moment I remove the wristwatch. So he's using it to regulate his BP. The moment something is wrong with his head, the wristwatch will alarm him that your BP is what is high. Quickly go for what? So it's regulating his BP through that. So this the output of nanotechnology. And this one is nanocar. It's already in the system. Some people have started using nanocar. So these are the output of what we are saying. So we can see where we belong. Many countries, they have gone ahead of us, but we need to wake up. Go to the next slide. The next slide now, this is for agriculture. Nanotechnology in agriculture. How do we apply nanotechnology? Now, currently, we got what we call novel food. This novel food, can you see now? It's a type of food that does not have a significant history of consumption. No history of consumption of this novel food. And produced by a method that has not yet previously been used for food. It has not been prepared by anybody. These are the procedure for preparing this food. No procedure. We call it novel food. One of it is canola active oil. The other one is what we call nano tea. This nano tea, we call it slim shake chocolate. It's already in the system. It's a product of what? Of nanotechnology. Go to the next slide. So, in the medical aspect of it, you can also apply it. This thing you are seeing there is this thing is nano robot. This nano robot is in the bloodstream. You pass it into the bloodstream to perform wonders in the bloodstream. So you can use it what we call hypothermia. Hypothermia is one of the applications of nanotechnology is for treatment of cancer. We can send some signals of nanoparticle into the bloodstream to be monitored by what we call an external magnetic field. It will send those drugs directly to the site where the cancer is. Then to discharge it there. It's much more effective than your chemotherapy. Chemotherapy, you take the drug, right? Orally, or in vitro, or intravenously. It's either they inject you, or they said somebody is having cancer of the lung, and they recommended drug for you for 6 months, 1 year. You are taking drug, almost 15 drugs every day. Morning, afternoon, night, morning, afternoon, night. It will get to a point that your system will become repulsive to what? To those drugs. Am I correct? Become repulsive to those drugs. And some living tissues may be invariably, in one way or the other, be affected. While you are trying to address the challenge, you are creating another what? Problem for the living tissue. And that's the essence of this nano drug. Very important. What we call it therapy, or call it hypothermia, using it to treat cancer. Then we also chemotherapy. This nano robot can be sent into the system. Just move directly, monitor it with external magnetic field to the site. It will just be there and discharge the drug. So the living tissue surrounding the cancer cell will be safe. So these are the application. Nanotherapy. All this one you are seeing here has been produced. All this one, they are what? They are cancer drugs produced from nanoparticles, and they are in the system. This one, paclitaxel, dorobizine, very common. These are cancer drug, nano drugs. All these ones, they are in the system, and they are very effective because they are highly targeted to the sites. So let's go to the next slide. We can also use for antibacterial and so on. Now, these are the objective, the application in nanomedicine. It's delivering a drug to a specific site in the body. One of the importance or the uses of nano drug is that it can actually target the sites. Now, if you look at this diagram, this one, this is an external magnetic field. Now, this nano drug is introduced intravenously into this body. All these dot are nanoparticles. It will scatter all over the body, and the target is this brain tumor. They want to eliminate this brain tumor. Now, if you continue to use your chemotherapy, you want to remove this brain tumor, the chemotherapy will circulate in all your system. But want to use this method called hypothermia. So you introduce nanoparticle intravenously to go through the body, to scatter all over the body. Then you will target it using this external magnetic field. Because these nanoparticles, they are magnetic in nature, they are sensitive to external magnetic field. So you can easily be attracted to what? Any external magnetic field. Anywhere the external magnetic field is, they move towards that direction. They just begin to migrate in your bloodstream, just like attraction. The external magnet attract them. So position the external magnetic field closer to the what? The tumor. And all of them will begin to gather towards the brain. You can see that we have just 3 here. With the help of this, many of these drugs have gathered here. So instead of them to be working here, where there's no cancer, they will all gather at a point where the cancer is located. And they will be more effective. They'll be more effective. That's the essence of this. Go to the next slide. So for energy, so I know majority of us are interested in energy. So you can see the different application. Now, in our lab currently, these two, we are working on this supercapacitor for energy storage and battery. We have these two established in our lab for battery purpose and for supercapacitor. You can use, as I've said the other time, these are the nanomaterial you can use. Both 1D, 2D, and 3D can be used for these applications. For supercapacitor, triboelectricity, energy generation, energy conversion, fuel cells, solar cells, energy conversion, energy saving, energy transmission. All these applications are highly possible. We can do them. All these, they are in the developed world. They are using it very fine, noiseless, pollutionless, and all manner of things. Solar cells, fuel cells, is in the system. We can actually use this nanotechnology to produce all this. Let me come over there. Okay, there's no need of it. Okay, let's go to the next slide. So you should work towards this one. Very important for supercapacitor, for battery. Next slide. Now, I will quickly show you few things we have done and what we are doing. This presentation is just to strengthen you. Let me just put it this way. To be able to prepare you ahead of what we want to do. So that's the essence of this preparation. Now, this is one of the publications with a collaborator somewhere in Pakistan. Impact factor of this journal is 4.0 currently. So we use what we call zinc ferrites. Zinc ferrites with graphene. Zinc ferrites doped with what? Graphene. For energy storage and for degradation of organic what? Organic wastewater. That's what we use this material for. So from this, we can see what we have done through it. Just go to the next slide. Let me just show you few results from this paper. We can see our XRD. I believe many of us will know how to obtain XRD from this. Now, what we did is to vary what we call the graphene. We want to look at the effect of this graphene on the material. We vary it from, if you look at it, 0.25, 0.5. We also vary with respect to the what? To the ferrite material. Let's look at the effect. Now, if you look at this, you will see the effect. It's also very obvious in our SEM. So look at the SEM. The one without graphene, the one with the first graphene, the second graphene, the third graphene. So look at the binding energy here from, so the binding energy, you can also see the effect on it as the concentration of the graphene varies, the effects is also observable in the material. Next slide. Then another result from this one is the reflectance, the energy band gap, the CV. Can you see the effect on the CV? That's the current voltage plots. So which we can do. We have this equipment in our lab. We can do it. So we are talking about energy storage. You have to start with the physical chemical the materials. The physical properties, the chemical properties, you have to obtain them. Then you'll now be thinking of application of it. Go to the next slide. So this is the photodegradation. How do we use this one for photodegradation? Based on the amount of or the quantity of the graphene applied to it. Look at this one. From 0 to 70. We have a polluted water. We want to use this nanoparticle to actually degrade what? The pollution. So we want to see the rate of degradation in the water. Now, when we use it alone, this is zinc ferrite alone, without the graphene, you can see after 70 minutes, the degradation is very, very low. Am I right? Now, when we had graphene for the first one, look at this one now. Can you compare it to this one? Look at the degradation. It's almost flattened. So look at the other one compared to this one. So if you look at it, you discover that when we added about, I think 0.25 graphene, or this one is much more effective. Am I right? In terms of degradation, almost flattens, which means at this stage, this level of graphene works fine for this material, for degradation. You can go further and produce this. Okay? So these are ways of application. Now if you look at this plot now, the C ratio C, you can see that this, which is this value, or the second value, has the better degradation. Look at the first one without graphene, up. Look at this level. You can see the level of degradation. So these are areas you can apply your materials and how to do. Go to the next slide. Okay, let's go to another article published on Material Today Communication. It's another powerful journal, currently 3.8. We also use zinc oxide. Zinc oxide is also a semiconductor. It's one of the one-dimensional semiconductor. We use this one for biomedical application and for photodegradation of rhodamine B. So it was published, I think, in 2022. Go further. Now, it was just one. We only carried out just one experiment. It was wonderful. When we saw the results, oh, this thing is really wonderful. Look at the SRD, very pure and wonderful. Look at the absorbance and the energy band gap. Very clean. Look at the FTIR, the Fourier transform infrared. Then we were able to obtain what we call nanorod. It was in form of nanorod. And we use it for that application. Go to the next slide. We use it for antibacterial application for those who are interested in nanomancy. And these are the results. We compare it with some standard drug that has been in existence. Ciprofloxacin is an antibacterial drug which has been in existence. Cipro, amozine, what are the other ones there? There are many. Amozine, ciprofloxacin. Now look at Cipro. Cipro is this one. Cipro, this is one of our drug, our nanoparticle. The first one, the second one, the third one. For E. coli, you can see Cipro is still very high. But when we come to Staphylococcus aureus, that you see that our sample is better than Cipro here. Now when we come to coliform, you can see that the three of them, they are better than Cipro. That's research. So if we now beginning to compare what we have done to the standard drug, Cipro is a standard drug and which we have been using. You can see that this one is also effective, which we can commercialize it. Okay? Go to the next slide. So we also use it for antifungi. This is for antifungi, and this is the result for the antifungi. And for photodegradation as well, this is the result for photodegradation from this result. Go to the next slide. Okay, this one, we published this one this year on solid state science, impact factor 3.5. So with this one, just to prepare your heart that we are here for business, okay? We are not just going to do things and put it. We want to have results after this workshop. We want to have results. So this is a collaboration. We did a collaboration work. So we combine the experimental aspect of it with the theoretical aspect of it. We introduce DFT into the system. We want to see comparison of what we have done in the experimental stage with what they will do in the theoretical phase and see if there will be what? An alignment in the two. So when we are trying to reproduce the result, this result, I did it in Pakistan. I did this one, the experimental something in Pakistan. And I called a friend. I said, friend, come. I've obtained this result. Produce the DFT for me. I want to see alignment between the theory and the experiment. Let's look at the properties together. if they can align. So when it generated DFT, then I was trying to compare. I said, oh, wonderful. I look at the band gap experimentally. I look at the band gap you obtain theoretically. I can see some alliance. I said, oh, good. So let's push it forward. I was able to push it in this journal. I submitted it once. Just scaled through once. Just once. So you can see how beautiful is it when you collaborate with people and when you know what you are doing, your work can move at a faster rate. Next slide. So a few things we did here is this. See the lattice cells. This is the XRD, the combination. This is the SEM and the crystal, the particle size. Go ahead from this one now. This is the Raman analysis. This is the energy band gap. And this is the VSM. VSM is about magnetic properties. We'll talk about the coercivity, the remanent magnetization, and what? And the coercivity, and the other one. So go to the next one. So this is the property now. So the band gap now, for each one of them, all we did now, we doped this material with nickel. We want to see the effect of nickel in this material and how it varies. When we did the experimental value, we saw that the effect of nickel was very obvious. Now, let's look at the theoretical aspect of it, how this nickel will be able to influence this material. And DFT was able to prove to us. From here, you can see this material, when it was not introduced, then when we introduce nickel into it, you can see the band gap. You can compare it with this one. You can see it. Then when we increase the value of nickel, you can see, and it was very obvious, and it's actually in line with what we did in the experimental setting. Go to the next slide. So, okay, this is another work. This one was done by one of my students, a master student, so which we publish in this journal, impact factor 5.4. So she actually used iron oxide for this application. So, and it was successful. We push it once and it scaled through. Go to the next slide, you'll see these are the outputs of this one, the XRD, the TEM, the particle size, everything, which some of us who have been working in this area will be familiar with this. Go to the next slide. So I use it for this application. We're going to look at a few of them today, or by the time we start our experiments, you will see some of them. Go to the next slide. Okay, this is another journal. Yes, this is where I want us to work now. So the group we have created, okay? This group we have created. So I'm going to give you this article. I want you to replicate it within 2 weeks. Within 2 weeks, we want to replicate something here, okay? This group, we're going to propose your topic. All through the night, you must be working. After this program, we must produce an article. I was dazed when we published this article, impact factor of 10.2. 10.2. I was doing my postdoc at NCP. This journal came as a surprise. It's a review work. That's why I said we have to start our homework. The young lady, this girl, Rabia, she's a Pakistani. She was doing our postdoc in China. I was in NCP in Islamabad. I was doing my postdoc. She saw my profile through ResearchGate, and she just mailed me through ResearchGate. That's, Dr. Samson, please, I am proposing this topic. Can you contribute so that we can write it together? I said, why not? I replied. I said, okay, send me the topic. Tell me what to do. She broke down the topic, the subtopic, and said, you write this, I will write this one, I will write this one. That was all. And that's what I want you to do in the course of this program. The topic proposed, subtopics. She just proposed this subtopic. You write this too. You write this too. You write this too. We put it together. 10.2 impact factor. If you have 5 of them, you become professor very soon. So it's possible. Am I right? Very, very possible. So don't despise little beginning. This one came just while I was working. It was even outside my working something. I just at night once I'm in my lodge, I started working on this. Maybe by weekend, I was using weekend to just get materials on this one. So it's very, very possible. Within 1 week, I was able to finish my own section. So you have more than 1 week here. So please, your own section, you must complete it. Is it possible? You must complete it. We are going to publish it, okay? So if you look at this work, role of keeping agents in the application of nanoparticles, his own is on biomedical, biomedicine. But your own may be on what? On energy conversion, okay? Whatever you want to choose, get me the topic tomorrow morning. Tomorrow morning, everybody, every group, you must introduce your own topic to us. The team leader will introduce the topic to us. So in your group chat tonight, that's what you are going to do through the night. You must harmonize the topic tonight. You must harmonize the subtopic, divide it into subtopic. At least we have 5 in each group, am I right? So if you can have like subtopic like about either 15 or 10, 5. Okay, 10 subtopics. 2 per person. Within 2 weeks, you can have a very perfect work. Okay? So please, group leader, take notes. We are publishing this work by God's grace. So this is very important. Our own for biomedicine and environmental remediation. We look at the recent trend and future prospects. What are we doing recently? That's the thing you want to do. In energy conversion, what are the recent things we are doing? What are the future prospects of energy conversion? If you want to use anything you want to use, nanoparticle, you can select a particular nanoparticle if you want to be focused. Maybe you want to focus on like zinc oxide. I single-handedly wrote one on iron oxide, only iron oxide, a review. I wrote it and I published in the European Polymer Journal. Skate through once. You can also do the same thing. You can focus, if you want to focus on a particular compound, you are free. Focus on a particular compound, application, recent things that is going on in that material. I hope we have network. Go and load your data tonight. Browse. Get recent articles. Go to Science Direct, okay? Type www.science.direct. Okay? When you get to Science, maybe when you create your group, add me to the group. Add the prof, add Professor Izim. I will give you our email so that we can follow you up as well. If there's any assistance, okay, we can give you any assistance, any guidance. Add me, add him, Prof, add Professor Fabian. We will continue to monitor your progress, okay? So any assistance, don't hesitate at all to ask. Go to Science Direct, you will see current journals. Go to Science Direct, type 2022 or 2023. You will see output of what has been done recently in that area. Then you begin to what? Tailor your work towards that. Okay, this is what they are doing currently. Okay, what can we do to modify this? What are the projects? What are the prospects now? You begin to think ahead. Okay, if we use this thing, these are the future world prospect of this material. And that's what you are going to write here. Very simple. Nothing less than 200 review. Nothing less than what? 200 references. If I can write up to 200 references alone, 5 person. If you at least 50 review. By the time you finish 50, then you get it right. Within 2 weeks, 50 articles. Review 50 articles within these 2 weeks. In that area, go out online, just browse, download as much as you can. Read through them, beginning to put your work together, okay? So please, we are working towards that. By God's grace, we will achieve it. So let's move to the next slide. So there are a few things we actually did there. This one is tailored on biomedical, just few things. Go ahead. So in conclusion, the development of particles that are nanoscale has created great opportunity in the development of improved drug delivery system, food system, energy and industries. Nanoparticle has provided an answers to many questions that cannot be addressed by conventional method. And lastly, nanoparticle is aimed toward to revolutionize the medical, the agriculture, energy, and manufacture industries. Next slide. So that's where we are in. You can see from here, as I said the other time, there is a projection ahead of us. There's a projection ahead of us. You can see where we are today. This is what? 2013, am I right? 2013. You know, if you check the road of 2020, the road of 2020 is like 100 lanes. Am I right? But as we are moving towards the recent year, it's becoming narrower gradually. And that's what nanotechnology is doing. They're bridging the gap. See, this man is walking towards 2024. Now, if you can imagine what will happen in 50 years' time, just have a projection. What will happen in the world in 50 years' time? Now, what is going on in the world should be able to guide us. Look at the war between Russia and Ukraine. Look at Gaza and Israel. It takes technology to be able to do these things. You can imagine you fly an aircraft unmanned. What is the brain behind it? Nanotechnology. Unmanned airplane, and it will go and meet its target and come back and deliver your message. Technology. So we are going there. So nanotechnology is predicted to alter the industry, the energy, agriculture, healthcare industry with novel method. And this novel method, that's what we are looking for. What are these novel methods we are going to use that this nanotechnology can actually predict this breakthrough? And we have to get there. So there are many things we need to use. So, and these are the challenges I'm posing to you today. We must start somewhere, okay? We must start somewhere. It's not rocket science there. It's about hard work. You have to do something, okay? So that's the last slide. Okay, go to the next slide. I think I will stop here for now. That's the first presentation. So these are just the preambles to what we are going to do. So we can ask questions. Maybe Prof, come. I think our guys are around. Okay, question. Okay, you can take your question before. Question. Let's quickly address it. Question.